So these are the new generation materials that we are trying to develop. An important part of any materials development I consider is multi-scale modeling, and the modeling point also was Professor Richard Catalog emphasized. That's an important part, and 2013 Nobel Prize was awarded for this multi-scale modeling. So we have a system, a nanoparticles, an example being over here, it could have a core structure, one medium, it could have a shell, it could have another shell, and they're all nanoscale built up. We want to tailor their properties and interactions. Well, you cannot treat them all from first principle, so the few thousand atoms you do by quantum mechanics, then approximate methods, and so this is what is called multi-scale. As you go further away from center, you use more and more approximate methods to calculate. So we do that, and then another one in materials design is materials informatics, where you can look at high input data, throughput data you have collected, and you can actually, Tara, is it okay? What?
Push the mic, please. Yeah, right.
Okay, so materials informatics, where you collect high throughput data and correlate the variation in any component and how it affects the property. Based on that, you can get a lot of information as to how you can make a material that will have certain properties. And that's what we did, area of materials informatics. So this is actually an extension of bioinformatics. Okay. And so these are some of the books that Tara was mentioning. We have written originally nonlinear optics, that is interaction of high intensity laser beam. Then I wrote a book on how light wave interaction can be utilized for bio applications. Then we talked about nano applications, and then nanomedicine. And these books are also translated in Chinese. So let me now talk about nanotechnology for global energy. As Richard mentioned this morning, nanomaterials has an important role to play in energy. So we are applying in solar energy, we are applying in hydrogen generation, hydrogen energy, we are applying in thermoelectric, and we are applying also in mechanical energy. What do I mean by mechanical energy? By changing the mechanical conformation, you can store the energy and you can use it like in muscle. Okay, so that's a mechanical energy, and in each case you can use nanomaterials to advance it. I'm going to give you an example of this and this. So nanotechnology for energy, Richard already talked much about this different sources of energy and how solar energy has an important role to play in this. So there is a lot of focus now on solar energy, and this thing will keep on expanding. So we are also working on that using nano technology. So let's look at the light harvesting material, which is the photoactive material, the key component of a solar panel or cell. So most solar panel uses silicon, crystalline silicon wafers to absorb sunlight and convert that into electricity. But there are other materials. Over here you can have gallium arsenide, and you can have the CIGS, which can be processed through solution. Cadmium telluride is what Dr. Dasgupta was talking about earlier, very high efficiency. And then as Professor Richard Catalog introduced, perovskite is a new class of material that has shown phenomenal promise. And the advantage of this material, as well as CIGS, is that they can be processed through solution. And you can use thin film technology to make large scale solar panels, or you can print them by using ink printing. So I think that this is has a lot of promise, because at the end of the day, it's not necessarily the overall efficiency, but dollar per watt, or how much cost you have to pay per watt. That has to come down. And if you're using thin film technology and very low cost solution processing that has advantages. So we are working, and one class is this, perovskite, like thousands of other groups, but our angle is a little bit different, as I will show to you. So this is the structure of perovskite, and it has organic and inorganic components. Organic are these heavy metals, and then is a counter metal ions and the counter anion, and then they are also interacting with organic amine group through this amine interaction with the metal. And this one you can process through different methods. One method is solution casting also. This has shown phenomenal progress, as you saw from his talk, claiming to 24% already. But there are some issues, as he brought up, reproducibility of a device, environmental stability. They're not very stable for a long time of term operation. And also there is hysteresis. And these are associated with moisture getting in the grain boundaries and other issues. So basically they are not practical materials yet. Okay, so we addressed that issue in a very simple way. As he pointed out, the issues are grain boundaries between these different domains, and the grain boundaries allow permeation of oxygen and moisture through them, and that's what deteriorates. So what we said, what if we use an organic diamine linker that stitches these domains and fills in there? So we make these, and we actually stitch those grain boundaries so that there is not much permeation through that of water or oxygen, and is prevented. And we showed already in a published paper over here in 2018 actually, that it highly improves the stability. So that's what's very simple application to address the practical challenge. The other one is to look at the solar spectrum. The current solar cell actually only absorbs like silicon in the visible all the way up to over here, which is around 1 micron. And so the IR photons, there are abundance of them, they're wasted. These invisible infrared photons are not harvested. And then here in this region, the energy is too high for silicon. So what happens is this energy is wasted because most of it is released as a heat. Silicon needs only this much energy. You give this much, excess goes as a heat. So what do? We introduce the concept of optical nanotransformers. So these are nanoparticles which can allow you to manage photon. How? Well, it can absorb these infrared photons and convert them by 1 photon to 1 photon, 2 photon to 1 photon in the visible. And when it transforms here, this visible photon and here can be more efficiently absorbed by silicon. Okay, that's one thing. Second one is that these UV and visible photons, which are highly energetic, silicon doesn't need that. So what we can do over here, that we can use these nanotransformers in a reverse way, where 1 photon absorbed here splits into 2 photons at this energy, okay, which can be more effective for silicon. And we call it quantum cutting. So we take 1 quantum of photon, cut it into 2, okay, more efficient. So this is principle of that, our nanoparticle design that uses rare earth ions. And so we produced nanoparticles, an example being over here by colloidal chemistry. So this is where chemistry comes in. It takes a light, in one example, 980 nanometers, and depending on the rare earth composition, it can convert that into green or red or blue. Okay, and this is the physics. So this is a beautiful example of physics, chemistry coming together to solve a technical problem. And so physics is there that you can, by 2 mechanisms, you can take a less energy photons, climb up, and emit a photon of higher energy that can be absorbed, or by energy transfer. Quantum cutting is the reverse, where the light over here is split into 2 photons. So here you can take a high energy over here and emit 2 photons. So this is physics combining with chemistry and guiding us how we can enhance the efficiency of these materials, these processes in a specially designed nanoparticles. These nanoparticles are 30 nanometers, and so they can be dispersed in water for biomedical application, or for energy application, they can be dispersed in a solvent, and in the plastic matrix you can cast, or even in silicon you can put a top layer of that. Okay, so we showed to him this thing, and thanks again, Richard, for introducing dye-sensitized solar cell. So where the dye is the harvester, we added the upconversion nanoparticle that converts IR light into the visible that dye can absorb, and we immediately showed enhancement of efficiency. Similarly, we added a quantum cutting layer, the down conversion layer, on the top of a silicon cell, and we showed that by cutting photons over here to produce 2 photons here, we showed 5% improvement in the efficiency. So this kind of photon conversion management is a beautiful way of adding value to whatever existing solar cell you have. It's not wedded to one kind of solar panel. It's just managing the photons from both ends. The hydrogen energy, we showed that nanoparticles can have having a large surface area, can be very, very active. So in this case, we said the silicon, Si, nanocrystals, which are 10, 15 nanometer in size. And we showed efficiently that they can react with water. Silicon has 4 valence, so it can interact with 4 protons, and it can convert into hydrogen. So in this paper, we showed very efficient conversion of water into hydrogen, and it is very much dependent on the size. If you go to more than 100 nanometer size silicon, the activity to produce hydrogen is very small. But when you go to 10 nanometer, so on, the surface is very active. There are a lot of surfaces, and they do that. Then we couple that with fuel cell and show that you actually can apply to devices. This is in this paper. All right. So now we are looking at what we call portable renewable energy. How we can actually harvest photons. We can recover the waste heat, as Richard talked about, through thermoelectric, and then we can store this into a storage device, which could be battery or supercapacitor. So we can harvest it over here in Jamaica, and we can send it to some cold place where it, through battery storage. So that's what the idea is, transportable energy, portable energy. Okay. Now let's move on to healthcare, the application to healthcare challenges. And here we are working on a whole range of diseases. As you know that we have many healthcare challenges at this time. We are looking at cancer, which still remains a problem. Some of them we have won, others we have not. We are looking at infectious disease and new kinds of infections coming on. And the most important one is that many of these infections are drug resistant, multi-drug resistant. Second thing is that many times they're co-infections. Like if you have HIV, you may be able to, may also be more susceptible to cause tuberculosis and other diseases. So co-infections around that we need to address. Addiction in the US is a big problem, opiate addiction and others. Obesity in the US is a problem, child obesity keeping up, and aging is, world's population is aging, so that age-related malfunctions. So we can address all these, we believe, nanotechnology. And so it provides us a new era of personalized medicine. We can design in vitro diagnosis, in vivo study of diseases and their progression, then therapy through drug delivery, gene delivery, and other areas, and combine the nanoparticle formulation with multifunctionality allows you not only to deliver these, and diagnose separately but combined way. So you can take the nanoparticles, target to disease site, diagnose, start therapy, and then diagnose again whether the therapy is working. And that combination of therapy and diagnostic is the term called theranostic. And so here we are talking about see, treat, and see. See the disease, treat it, see this effect. Okay. And this is an example of our multidisciplinary collaboration in the area of nanomedicine. Professor Gene Morse, he's a pharmacologist. These three are actually four of them, are practicing medical doctors. We work with them in different diseases. And we have engineers and biomedical researchers. And so it's a combination of team, and myself being primarily chemist providing nanomaterials. We work together. So what does nanomedicine offer? Unique properties of nanoscale. Some of the properties are size dependent. Then we can, the same nano formulation, we can make multifunctionality, more than one function it can perform, either by core shell structure or by changing the composition. We can have targeted deliveries. We can put targeting group on a nanoparticles to target to disease site by recognizing the signature of disease, like on a cancer cell. Okay, and then we can have controlled release. So these nanoparticles we are trying to work on, we introduce functionalities, optical, radioactive, magnetic, heat, and a whole bunch of them. I'll give you an example of that. So what are the nanocarriers requirement? Well, first of all, they need to carry, many of these drugs are poor water soluble. They don't disperse very well. They're hydrophobic. So you need to encapsulate to make them hydrophilic surface environment of nanoparticle to disperse. They can protect those drugs from enzymatic degradation. Then they can be targeted to a specific site, organ, or cell. Then we can have controlled release. We can do diagnostics and therapy together. And eventually you want to make sure that the nanoparticles are safe. So they should be biocompatible, and they should be eliminated from the body. They should not stay in the body for a long time, because who knows what kind of problem we can create. So we work with a number of different formulations, polymeric nanoparticles, liposomes, dendrimers, inorganic nanoparticles, which are core shell, or could be core shell decorated by antenna connection to organic molecules. So these are the ones. Then on the surface, we can put targeting group. These are antibodies and so on that can look for the signature of disease. So in case of cancer, the cells have antigen expression on the surface. And these antibodies are looking for that antigen to grab onto and to get into the cancer cell and leave the healthy cell alone. Okay. So here is what we do in our lab. We have in vivo imaging system, optical imaging in one area. So we can actually take those nanoparticles which are carrying the payload, that could be drug, could be other things, and they have targeting group. So we inject them into tail vein of a mouse, and then a few hours that has tumor grown. In case of cancer, we grow a tumor in this mouse model, and then after a few hours or so, you would expect these nanoparticles by targeting will accumulate here. And if these nanoparticles can light up by shining light and giving you emission in the red region where the body is transparent, you can, through optical microscope in this in vivo system, you can actually see those nanoparticles are localized there. Then you can do therapy. So what kind of therapy? The nanoparticles we use in our lab, metallic or organically modified silica, silicon, polymer, over here up-conversion nanoparticles. And for diagnosis, we are looking at imaging and sensing. Therapy, we do chemo, gene, and immunotherapy. The Diseases, we are looking at tuberculosis, HIV, cancer, addiction, influenza, and brain diseases. So one example of TB treatment is that we have this polymeric nanoparticle formulation that has a hydrophobic core, which is PLGA, and then a biopolymer called chitosan is in the shell to make it, because it has a hydrophilic group, this nanoparticle can be water dispersible. Okay, so we encapsulate the TB drug inside the which is hydrophobic, this chemotherapeutic drug in the PLGA, which is hydrophobic, and then we can attach beta glucan, which does two things. One of them, that it targets to the TB bacteria, and then the cell which is holding it, macrophage, and then it also provides immunotherapy. So it boosts the immune response. So these nanoparticles we actually have already shown that they are taken up by the cells, and they are effective in releasing the drug and more effective in tuberculosis treatment. This paper is also published. I don't have a reference. So now let me talk to a last biomedical application, which is nanotechnology. So as you know, the brain is now a focus of many medical research now. Our country has what you call brain initiative, and globally it is an area that is really now re-emerging. And John said when he was working in his PhD, he started neuroscience, and so he was a very pioneer earlier days, and so we are now coming back. So the idea is that can we do functional and structural imaging using multimodal platform, a nanoparticle in vivo targeting, tracking, and then if we want to deliver across the brain through injection, they have to cross what is called the blood-brain barrier, which is there to protect you. Okay, so those nanoparticles we designed that they can cross. We can in vivo, we can see an in vitro models that they are crossing. Then we can do image-guided and externally controlled gene therapy, chemotherapy, stem immune radiation therapy, a combination of that. And then we can also do optogenetics using light stimulation of neurons to fire them. And then, so this way we are looking at functional imaging and mapping and modulation of brain activity using nanoparticles. So that's one of our area. So one example I want to give you, it has two purposes. One of them to show that indeed these nanoparticles can be crossed through this blood-brain barrier model to show that they cross. And we also did that in vivo to show that they cross. And then they localize in the case of brain cancer, which for glioblastoma in the tumor. And then they release this drug. This drug is natural, curcumin, which is an important ingredient in turmeric. And turmeric is released, and that do indeed shrink the tumor as we monitor by imaging. So fairly effective in glioblastoma, but also we are now recently finding that it's effective in Alzheimer, to breaking these amyloid plaques, So we are very excited about it, and I think that there is a lot of future in using natural medicine being delivered by nano formulation. Okay. And this shows to you one of them where we are using light to stimulate neurons through optogenetics, but we need on the site in membrane, we need a blue light. However, blue light doesn't penetrate deep through biological material. So we use our optical nanotransformer, shine 980 light, which can go deep, but on the site where it sees this nanotransformer, it gets converted to blue light. That blue light now can stimulate the neurons. So we have also published this paper 2017 showing this kind of optogenetics, upconversion optogenetics to stimulate neurons. So here is the area we are now talking about neurophotonics. We use light to image and produce, modulate brain waves. We are talking about the area of neuro and photonics combined. And here we are utilizing functional imaging, but also mapping of brain waves, which generates a magnetic field through magneto-optics, new generation magneto-optic material that can sense the very weak magnetic field of the brain. So here is our imagination. Can we quantify and enhance cognitive state of mind, which affect Alzheimer? We are looking at traumatic brain injury due to sports or military, or due to cognitive deficiencies in children, which could be autism and retardation. Can we detect that and through this human-machine interface, and can we actually quantify it and then enhance it through optogenetics and other treatment methods? So this is what we are working on. This is our dream is that identify and treat cognitive deficiency from very early stage even. And that's what I call that I'm a dreamer, and I want all of you to be similarly a dreamer in this area. Okay, so then the other one, I'd like to pose this, which is my imagination and dream. Can we live for 1,000 years? And the answer is yes, there are clear pathways. And I'm only saying, can we live, not should we live? That's an ethical question. And here, we can use nanoparticle. I have a chapter in this book which can remove, scavenge free radicals, heavy metals, do neurological repair, provide growth hormones, and replace the shells and tissues that are damaged. And with that, we are, again, rejuvenated. So it is possible. Okay, now the other two areas I want to touch on is we are also expanding cyber-based telemedicine. We're looking at wireless control, diagnosis, therapy, and patient management. And here again, nanoparticles can play a role because they can be relay things. So RF-initiated diagnostic penetrant monitoring, RF-activated control therapy, working on wireless control or robotic surgery, is another area, cyber. And then another important part is that we need to be secure. So security, patient information, transfer, all these are important issues. So this is the thing, management of patient information is a very important area. The other area I would like to touch is artificial intelligence, where we are looking at using, which I consider a very important role, because we can have a machine learning discovery platform to enable users to navigate through massive tons of data and acquire knowledge. Collaboratory, providing a cyber infrastructure that will involve sharing, exchange, and analyze data. So we have post-patient data, human intelligence from different sources, artificial intelligence advancing computing platform, and active learning to predict and diagnose diseases. So this is going to play a very important role, and our place is very deeply involved in. Now let's talk about commercial opportunities. I really feel that the academic people should not just focus on intellectual gratification, but how we can really go extra distance to transform this to a technology that benefits society and create high societal impact. So one aspect we say for that, you need to think outside of the box. The second one is that you should focus on high societal impact, and there you're looking at innovation and technology transfer means, and then you need to form global partnership. I want to give an example of among the 9 companies, this is the one that we really a real success story, and this is on using this concept of nano clinic, which was inspired by 1966 fiction of a nano submarine taking the medical doctor's personnel to a disease spot. We made this nano bubble, nano clinic with targeting group that drives it to the cancer site and releases it to activate therapy. It formed the basis for a company which was licensed Nanobiotics, and that company now, with successful clinical trial, is 300 million euro company in Paris, Paris-based. Fortunately, I have a tiny share in there too. It's a real success story. So what I want to tell you, entrepreneurship. Okay, I'd like to promote that, and I want all of us, not just to stop at publishing papers, but take it further beyond. And so inverters should not run, but these are some of the lessons. If you're an inventor, don't try to run a business partner, a business group, or license to a company, or form alliance with somebody who has a business degree, because we are not good at running business ourselves. And for a material-based invention, it's very important that these materials be scalable. Don't make a small amount and say, hope that somebody will use it for technology. You need to show a pathway for it being scalable. They should be reproducible so that properties can reproduce, and they should be environmentally friendly. The technology must compete successfully. So this is where inventors, they consider their invention the most fabulous thing that has come along. This is their child, the most beautiful child. But so they're not objective. And you need to look at what is existing over there. Don't wait for somebody to come and say, oh, this is so beautiful, I want to license it. You need to do your homework too. So that's another one. So you must compete. Do not offer a one-stop shop. Don't say that we can do everything. Form an alliance, partnership, and world economy is global, so think globally. Use stage financing, not outright venture capital. You need to start with a small funding. And so let's talk about another, promoting entrepreneurship in academia. You really need to change the culture. I have traveled across the world, and luckily now in the US, we are changing the mindset of academic people and the students to think about entrepreneurship. But many countries are still there, that's not in their mind. PhD students want to finish PhD thesis and publish papers. Professors want to publish paper, go to conferences. So we need to change that mindset. So with that, you can do by educating, encouraging, assisting those interested in technology transfer spin-off. Now, how do you create a startup? So we should have a startup funds. And I gave 2 examples. At our university, we have a fund called Bruce Home Fund. This is a seed fund we provide to aspiring students who want to take the technology to marketplace. We say go and find a student from business school or from entrepreneurship training, and 2 of you submit a proposal for this. And then if we review the proposal, we like it, we give you money to start. There is no obligation to pay back, there is no obligation at all to share the profit. So that's a good start. And the other one is the government-assisted small business innovative research program, which is can give you. I have 2 companies that advance technology by getting more than $3 million from the U.S. government, and I owe nothing to the government except that they could use the technology when they need it, but they have no share of money and profit coming out. So that's an easy way also to start. Then bring industries to the campus, start industrial training, provide testing to solve their problem. This way they actually develop confidence in academia, that academia is really serious to partnership, So this is a very important part. And then I like to also say that at our institute, there is opportunity. I'm done. Tara, I'm done. So educating, training, and research. So those people who are interested in PhD or postdoc, short-term visit, you can write to us. We have opportunities. We have opportunities for business development. We have opportunities in collaborative research, and we can jointly apply for different funding in different places. So these are some of the things. So I want to leave you with this message: advancing the frontier for high societal impact. You need to have a global vision. Multidisciplinary training and education is a very important part, and we need to think with transformative approaches to make breakthroughs, not incremental. Okay, and then changing the culture at academia to engage in economic development. That's a very important part. So here is the cartoon diagram, thinking outside the box for this. You need to go outside of the box. These are our collaborators. Some of them are listed, funding sources, and I thank you very much.
Thank you, Parag. This is a very, very excellent talk. Can you take some questions from anybody? It's so clear.
Yeah, well, I hope. I hope.
I just have got one question that is it all a thought process, or you have got achieved something tangible, which is really in the health sector or in the
We saw that
solar
already in nanobiotics.
Yeah.
That's a clear, tangible thing.
Mm.
The other one with Thermo Fisher, the partnership,
instrument.
Thermo Fisher, the partnership we
Yeah.
had. We have that instrument for sale. We are already now negotiating a deal with Russia to sell that Raman spectrometry biomolecular analysis. So we have with that example of what you call diagnostics and cancer therapy. Look, the thing is that in therapy,
nanoparticles
yes,
that targeting the particular disease, tumor, or is it been done?
oh yeah, this is a routine thing. You take a nanoparticles, and then you need to understand the biorecognition principle. So what are the signatures of a cancer, specific cancer? Then you can design a targeting group that has affinity for that signature, okay? And so that could be antibody, it could be aptamer, it could be peptides, it could be a small molecule, like, there are folate receptors, so you can use folic acid, you want to target. And so then you can attach to chemical conjugation the surface of nanoparticle, these antibodies, and they can go hunt around, look for the signature where they attach to the cell, and the cell by process called endocytosis grabs and goes inside. The
What kind of
nanoparticle.
nanoparticles you using?
List of things. See, there is no single magic bullet.
No. Is it?
Thank you, John. There is no single magic bullet.
Yeah.
So you use a nano formulation that is actually more suitable for that disease. So, for example, glioblastoma, I showed to you this polymeric fluoronic encapsulation
right.
that very readily disintegrates and releases the drug. And then in the case of tuberculosis, I showed to you a hydrophobic drug which gets encapsulated in PLGA polymer and then is coated with chitosan. And chitosan has a targeting group to make it water dispersible and target. And that one was for tuberculosis. So I think that we have utilized different formulation that is most suitable for that application. Okay, similarly, we can tailor the nanoparticles which are more easily able to cross the blood-brain barrier to go to the brain therapy. So I think that the message again is that there is no single magic bullet.
Yeah.
That you use one bullet for all applications.
Yeah.
Well, first, just a comment. I really enjoyed your talk. Some very nice.
Thank you.
Sound. I especially enjoyed the kind of photon engineering to improve the harvesting of sunlight. That was very, very neat. But I also had a very general question right at the end. You talked about changing the culture in academia, but don't you think a lot of that's happened already? I mean, I think a lot of that has happened already.
Yes,
But I mean, I know
happened.
UK universities have been transformed in that sense, to the extent that a head of department, I'll not mention which university, complained to me about a year ago that he was getting fed up that so many of his members of staff were not in the department because they were away running their spin-out companies. So I think it has. So I'm not saying, but I think it has shifted really quite a lot. I mean, I'm obviously speaking more
No, I
experience.
think you are right. In some countries, it already in some countries it already has happened. Like in the U.S., it's really now common policy. Every university, they encourage the professors, don't rush to publish. If you see that it has intellectual merit value, send it to Technology Transfer Office. We will evaluate, and the least we can do is file for provisional patent. Okay, so, but I give you an example of a country like Russia. I have a very strong interaction with this university called MIFI, and I go over there. They don't know what to do about this technology transfer. There is a mistrust over there between industry and academia. Academic people, they just play around.
Same here.
So there are some countries in India, same way I was there 1 month ago with big nanomedicine conference. They are struggling with how they can bring together academia and industry or business group. So some countries still the mindset is the same, that professors should be intellectual. Do not dilute your intellectual innovation by trying to get into business. That's the kind of mindset. I'm sorry. Sure.
Yeah, just quickly related to that, because I know other persons want to ask questions. Do you find that this huge gap between applied research and basic research in your travels? I mean, that's probably not the situation at your university, but how prevalent is that thinking still?
I think that gap is narrowing, so there is a continuum now. Before it was that if you were in science, physics, and chemistry, and biology, you were doing fundamental science, okay? And if you're in engineering, or vocational school, you are more into applied, okay? Now there is a continuum, so we work on developing fundamental concept, but we don't stop there. We say, well, can we take it further? How can we apply? And one example is that we took the physics of up conversion and down conversion, and we said how we can guide it to make materials. Now the question is, these things open up for solar application, for healthcare application, and these are applied. So here is transcending something from fundamental concept all the way to there. And that pipeline requires, again, multidisciplinary integration.
I saw some questions. Yeah, Thomas.
The Sbir Grant, is it something that it does for the US or US? Is it just US companies, US technology? For the Sbir Grant.
SBIR grant is, and other countries have similar grants, but SBIR is in the US, and it is only to help a small company or entrepreneur who are trying to spin off in the US. So this is a requirement. Not only that, but the company's owner has to be more than 50% US, there. So that's another requirement. It's just to boost the US economy. And it's very nice because they give you first phase 1, which is 200,000, roughly that level, to prove for the proof of concept. Once you actually demonstrated that this is viable and could be viable business, then they ask you to submit phase 2 with a business plan. That could be up to $2 million. And this is, again, for you to develop. You don't owe anything to the government. Then there are other grants which are for academia and industry partnership. So there is based on matching. The industry can put certain percentage, generally half, and then the government will give you half to match and do together co-development.
Anybody? Anyone? Any questions? Then thank you very much, guys. Oh, sorry. Yep. Yes. No. Usually, we are giving you on behalf of CAST.
Organizing community and CAST, so this is one of the one of the. Thank you,
That's the token of appreciation.
Thank you.
All right, thanks very much.